before the toll break even, right? So back then we were taught to do a two-sample t-test by comparing two means with each other, right? Now I compare more than two means, and somehow these things ought to be related. Because what I just presented to you by the f-test, where we compare the means with the overall mean and then do the f and all that, I could also do that if there were only two groups. There's nothing in what I told you before the break that couldn't also be done for two groups, if you want. It's a kind of indirect comparison of two groups, but still it could be done. I mean, and the formality of it you see here. Let's dwell on one thing first. The computation of the within group, this was the within group fluctuation. The sum of squares for residuals, the error sum of squares, many words for the same thing. Actually, even though it might not appear like that when we looked at the formula, but remember it was a double summation. The definition of SSE was a double summation, where actually the sum of squares for this could be expressed as this weighted average of the original variances, or said differently, that was a bit not so directly expressed. In the case where all the ni's are the same, that's like we saw in our three groups of 4 data points, the toy example, right? I could compute the variance in group 1, the variance in group 2, the variance in group 3, each of them separately. And then I could take the mean of those 3 variances. And that is exactly the MSE. So the MSE, the mean square error, is to be thought of, and when the n is the same, it's exactly the average variance within the groups. Right? MSE expresses the average variabilities across the different groups. So it's a average within group variability. So in the two-group setting, it corresponds to averaging the two variances. And this is actually the version of the two-group setting which we only mentioned. We didn't really use it back then, but we mentioned it. That we had, when we do two groups t-testing, we use this variances each separately in the computation. S1 and S2, that's the so-called Welsh version of the t-test. It makes good sense to not actually average the variances. But now we have an additional assumption going on. We do assume that it makes sense to average those variances. We do assume that it's the same underlying population variability in those 3 or more groups. It's a non-trivial assumption like in the regression setting, but we do assume this homogeneity of variances. It's one of the classical assumptions. So, at least if we let T-ops be the so-called pooled version, equal variance version of the two-group t-test from a few weeks ago, which we recommended generally that we didn't have to think about, we didn't have to use it. But this is where the explicit link goes with what we do now. Then the F that I have showed you is mathematically equivalent to the t-test statistic, to the pooled version of the two-sample t-test. Right? There's a mathematical exact equivalence there, such that the statistics you do would be exactly the same. That's the link. And the new thing is, now when we move to multi-group analysis, we impose this additional restriction or this additional assumption that we assume that it makes sense. We didn't have to in the two-group, but now we have to, at least for the basic set of tools. So that's a bit of background, just for the record. Now back to back to the actual business of doing the analysis of some data and extracting the relevant information from such a multi-group data. The term post hoc analysis is used within analysis